All right, good morning. Talking about roller coasters or exams over here? Gotta cry. Okay. Okay, so today want to talk about hardness and alkalinity so that we can kind of be prepared, have the fundamental pieces in place to talk about softening water. So I mentioned and showed us this graph earlier in the semester when we were kind of giving an overview in water treatment. Hardness is one of those properties of water that is really sort of optional to deal with for most cases. If you're dealing with a system where you have really hard water and then an industrial application requires that mineralization is not occurring within the equipment, for example, then that industry might have more than just an optional perspective on it. So some industries, or some equipment using water is going to require soft water so that it can avoid being ruined by mineral deposits and then clogging of certain things or stuff in that regards. So softness or hardness there then is optional in terms of drinking water quality for health purposes because it doesn't really affect anything. Maybe there's a little bit of taste. Maybe you get some useful minerals out of it, but typically when we're talking about hardness, we're really referring to primarily magnesium and calcium. And I don't think that's really a typical source of those minerals for our diet would be the water. So it's really not something we think about in terms of health, but rather convenience. And then specific industries might have to study what kind of water source they're using and adapt it accordingly. So they might have their own water treatment to remove the hardness. Okay, so I'm gonna take this off real quick. So what we'll do then, and as we see here, is consider that it can be variable, and we basically want to know how are we even describing this hardness in a way that we can quantify, and compare. If one system has a bunch of calcium, the other system has a bunch of magnesium, what do we do about it? How do we compare it? What are our tools for this aspect of the trade? So most of the time, when we talk about hardness, we'll talk about it in one of two ways. And we're going to go in depth on both of these, but as a quick overview, we have milliequivalents per liter. So we see right here, MEQ per liter, or milligrams per liter as calcium carbonate. And these two are convenient. One is kind of on a molar basis, that milliequivalence ultimately boils down to milliequivalents of charge in a sense. So we'll talk about that. The other is essentially a comparison. So milligrams per liter as calcium carbonate. Well, it turns out that calcium carbonate, if you were to take the molecular weight of calcium carbonate, CaCO3, which by the way is, calcium will be 2+ in solution, and CO3, our carbonate, is going to be 2-. So it's a pretty common form to talk about calcium carbonate, and you've probably seen it in a lab or something. This is a very common substance, and you put it in water, you get calcium carbonate, right? So it turns out that the molecular weight is an even 100 grams per mole. And so given that it is calcium and carbonate are both important in our hardness and alkalinity system, and that's such a nice even number, it turns out we use calcium carbonate very often because it's just so convenient. Okay, so we'll see it become convenient in a variety of manners, and we'll compare other things to this calcium carbonate hardness as a metric. And so we're going to describe things such and such milligrams per liter as if it were calcium carbonate. That's kind of how we will think about it. Okay, so there's a couple things there, and if we were to go back and look for the units on this particular graph we looked at earlier in the semester, you'll notice that it says concentration of hardness as calcium carbonate. So we see it there, and we'll see it in a lot of places. So today, primarily what I want to talk about is the carbonate system and these aspects of quantifying hardness. Okay, so refresher on the carbonate system. Real quick, before we dive into it, if I were to ask you to solve for the pH of natural rainwater, have you done that before in some other class? Okay, some yes, some no. So basically, if you've taken the aquatic chemistry, right, that's a 3145, or is that the other one? If you've done it before, what class was it?
It would have been a 3145.
But you didn't. Okay. Choosing words nicely. Okay, so some familiarity, but definitely like not something you feel like you could do today, right? Is that accurate? Okay, so I want to get us to the point, kind of remind us and talk about it to the point where hopefully we could solve it, or at least understand the process and deal with equilibrium systems as we know we need to with chlorination anyway. But to elaborate a little bit, I don't care so much that we have expertise with the ideal gas law and Henry's law. It is pretty straightforward. So I hope that you can be given a simple problem and make use of it if needed. But we're not dealing too much with Henry's law and all that. It is relevant for water stripping, for ammonia stripping, for different processes for the carbonate system and all that. So I expect and hope you have some understanding of that, but I'm not really going to focus too hard on that. Right now, what I want to talk about in terms of the carbonate system is sort of you might call it acid neutralization capacity of water. That's another term for alkalinity in a sense, or maybe a bit of a synonym. Really, the amount of carbonate, so CO2 that's been dissolved in water, is going to act as a buffer for the pH. Because when you have a bunch of carbonate, and the form of carbonate is going to be pH dependent, and then you change the pH by adding some acid or base, it's going to cause a shift in the carbonate, and you might get some that will then leave as gas, or maybe you'll have more dissolve as gas, gas dissolving. So the carbonic acid and carbonate system in general relates to the addition or subtraction of hardness and acid and base. So all of those things are somewhat connected, and I want to dig into that a little bit. So as a reminder, we can have CO2 gas, which is in our atmosphere, dissolve as aqueous CO2, as written here, as we have molar concentration here of dissolved CO2. That's going to be in equilibrium, or with, if we let it reach equilibrium, with the atmospheric pressure of CO2. And this is the Henry's law. So we have a Henry's constant there, the Kh, that is describing the relationship between dissolved CO2 and the pressure of that gas, right? The pressure of CO2 in the atmosphere. And this would be a Henry's constant. How about it? Okay, so that's going to give us some source of carbonate. And what it's going to do is it's actually going to dissolve when we react CO2 with water. What we end up with, and this is going to be equilibrium in a sense with the Henry's law, we're going to end up with H2CO3. because we had two O's here, one O for the water, two H's, and one C gives us H2CO3, right? And from there, then we go through our equilibrium with that carbonic acid. So in a way, it kind of sequences from here, from there to the bicarbonate, HCO3 minus, to the carbonate. And of course, this is in equilibrium. So these guys can also go back up. And potentially, you could also have off-gassing of CO2 from water if you overloaded it with CO2. So you could add a whole bunch of some form of carbonate, and maybe you get a supersaturated solution of carbonic acid, add that to water. A lot of that will leave as CO2 gas if you let it. In fact, that's basically what's happening with a soda bottle. You inject a whole bunch of CO2 gas, pressurize it, close the container, and then if you keep it cold, the gas dissolves more. It's the water or the solution, the soda, can hold more gas, and so the fizz is a little bit more stable. But if you heat it, that gas wants to come out of solution. So if you were to, let's say, microwave a bottle of soda while it's capped and sealed, eventually you're going to reach a point where the gas just expands so much, leaves the water, and it makes an explosive mess, right? I think that's similar to what happens when you add Mentos. It kind of catalyzes the gas leaving the solution to a soda bottle. Okay, so then thinking about and I've got actually some pictures of that, but coming back to the carbonate system, if we think about the fact that when we add CO2, we get this carbonic acid, that's going to be a non-charged form, and that's going to be the form with the most hydrogens, right? H2CO3. And so that's going to be the form that's on the most acidic side of our pH spectrum, right? So if we make a graph of pH and we look at, it says log A here. What it's talking about is the fractional form of the carbonate. Is it, what fraction of it or what portion of it is in the H2CO3 form versus so that's carbonic acid versus the bicarbonate HCO3 minus versus carbonate CO3 2 minus. Okay, so if these little alpha 1, alpha 2, that's literally what it's showing here is the portion that is bicarbonate. So the log of that fraction is one way to represent it. You could just do that fraction. We would have to have a little bit of a different scale, but we're on a log scale here. And so we see this is, if this is bicarbonate, this middle line here, and the fraction then is the bicarbonate divided by each of the carbonic species, carbonic acid, bicarbonate, carbonate, that's all we're saying is this is the fraction of the total that is bicarbonate. Okay, and we could likewise do, well, in fact, it does a 0 here, the H2CO3, the fraction that is carbonic acid, goes all the way up through here, right? So that's why I drew on the left, we've got that H2CO3, on the middle, it's HCO3 minus, and on the furthest right, this is the condition where we have the least amount of H plus around, and so we have the least amount of H's on our molecule, right? That's kind of the way the equilibrium is working. If we push our pH way up high, then basically any H plus that was around that could have been taken away has been taken away. That's sort of how you can think about it. Because we just have so much OH minus, it's pushing, so OH minus is dominating up here. It's going to react with as many H pluses as you can to reform water based on the equilibrium of water itself with H plus and OH minus, right? And we know that has a Ka. You should commit this to memory if you don't have it already. Ka for water, and I'll just call it Kw for the equilibrium constant for water, is 10 to the minus 14, which is why pH goes from 0 to 14. Okay, so this is the carbonic acid system. or the carbonate system, these are in equilibrium and these are in equilibrium. And so all three will be in solution at any given time. But usually one or the other is most dominant, right? And if you think about it, even when two are equal, these two are equal, there's a very small portion that happens to be in the carbonate here, for example. It's 10 to the minus 4.5, right? So the fraction that is this thing is, you could take 10 to the minus 4, 5-ish. So 10 to the minus 4th, that's 0.0001, right? So 10 to the minus 4th, that's the fraction that is carbonate at that pH, which is 6.5-ish, 6.3. So very, very small portion is carbonate. But the rest of it is approximately 50-50. So this would be like 10 to the minus 0.4 or something. That's going to give us approximately 0.5. And that's when those two are equal. Likewise, that's when at pH 10.3 or something is when these two are equal. So it's just like our chlorine system. It's an equilibrium system. We can map it as a function of pH. Just want to be kind of give a good overview of that. And in fact, we have the pH values given here. That's pH 6.35 is where these two are equal, and 10.33, these two are equal. Okay, any questions on that? Is this making sense? Okay. All right, so a bit of an elaboration on each of these reactions. Kind of talked about these already. CO2 will react with water. That'll give us the carbonic acid. Is technically in equilibrium in an open system. Sometimes we'll have a closed system where we don't allow any exchange with the atmosphere. It's just a bottle that's all the way full with water. There's no more gas allowed in it. Technically, you could also call this a closed system with headspace, but I guess the simplest closed system would be if I filled it all the way with no headspace, right? No gas up here at the top. And that would be a fully closed system, and that would let us say, okay, well, this is not actually in equilibrium. We just have this amount in the system. So we could cross this off for a closed system. Would prevent and I'm going to say with open atmosphere, because technically we could maybe say we have some extra special pressure in the headspace here or something. We won't go into all that, but it will be important to recognize there are closed systems and open systems. Typically, if we're dealing with a problem that's elaborating on kind of a lot of the pH and how that's affecting the rest of the system, a lot of times we will assume it's closed. For the case we'll take a look at today, how we would solve for the pH of natural rainwater, it obviously has to be an open system because it's open to the atmosphere, and we want to account for how much CO2 is in the atmosphere. Okay, with that carbonic acid, that's in equilibrium with bicarbonate. This is why we call it carbonic acid, is because it's going to release that proton, that acid, by that reaction, and that could go further and release another one. And this is really why rainwater, if it's pure rainwater in equilibrium with our atmosphere, should be slightly acidic, because we're going to dissolve the CO2 into it as carbonic acid, and that will become in equilibrium. You know, if our default was pH 7 for rainwater with nothing else in it, well, pH 7 is right here. And so to get there, we started with the H2CO3. We have to release some protons. And so that's actually going to shift the pH left by doing so. And so a little more of it will be H2CO3 form, but they're both existing. And so regardless of what happens, since they're both going to exist in water, you're going to have some acidity there. Okay. So we'll come back to that concept when we take a look at that example of solving for the pH natural rainwater. Okay. Of course, we also have the same reaction here, or the same equilibrium setup. Bicarbonate will be in equilibrium with carbonate, especially relevant at higher pHs. Okay. The book also describes a case where maybe we are adding carbonate in a different form. So calcium carbonate, like we talked about, the hardness situation. If we do add that, maybe a solid or something, essentially what we're going to have is, in this case, if we add calcium carbonate, or there's maybe some mineral like lime, essentially calcium carbonate, if you have water passing over some limestone, then you're going to have an equilibrium here that's adding some calcium and some carbonate, or you could have it, this is a solubility equilibrium, right? It's either solubility product there, could be remineralizing that solid. Okay, so it could go either way. Sometimes we might just add a certain amount of calcium carbonate and we assume it all dissolves. If we're under the solubility limit, we might have just all of that dissolve, and then that would be that. Or if we have some solid form, we have to deal with that equilibrium as well. So in a natural system, that might be fairly important to recognize, like the mineral content in a natural groundwater or something. Okay, so just to elaborate a little bit on the equilibrium equations here, we can call it K1, K2, and K. I guess they're recognizing the solubility here, so this would be a KSP solubility product. For K1 and K2, those two will govern these two equilibriums, right? So this would be K1 and K2 from that following page, and we'll see exactly that they're referring to the equilibrium between H2CO3 and HCO3 minus, and then the second one between this guy and carbonate. So here, this is the products over the reactants for these two equilibrium. So right here and right here, we could actually just write up here, this is K1, governed by K1, and this one's governed by K2. Okay, so that's what these are referring to. And because we write any of our equilibrium constants as, let's say Ka, for example, this is, if you recall, the A to the A power times B, excuse me, it should be the products over the reactants, so I'm doing this backwards. Should be C to the C power over D to the D power divided by the A and B if we have A and B. And that's for a generic equilibrium reaction where we have A amounts of A, B amounts of B in equilibrium with C of C and D of D, right? Okay, so that's our, just a reminder of the form here, and that's where we're getting these two equations, K1 and K2, and then it's giving us standard values for those equilibrium constants at presumably standard conditions, so kind of room temperature. There's a table that the book provides. Technically, we could calculate these for different temperatures. I'm not so focused on that. That is, probably would deal with that in the chemistry class with thermodynamics of the reactions themselves. Okay. A little bit more about that here. It's kind of just taking it a step further, showing us here if we are looking at our carbonate system here, might be kind of interesting to compare how these relationships are set up by simplifying according to K1 or K2. So we could say that the ratio of carbonate to bicarbonate is equal to K2 over H plus. We can see that if we come back up here And if we were to solve this guy for the ratio of carbonate to bicarbonate, right? And that ratio will give us a way to solve for what percentage do we have of one or the other. We've actually done this with the chlorine a time or two already. So that ratio can be pretty helpful. That would be K2 over H plus. You could write that as K2 over 10 to the minus pH. And then we could take that and put in some values, or simply just simplify, put in the K value there and say that's going to be 4.68 times 10 to the pH minus 11 here, because this was 10 to the minus 11 for that guy. Right, so that's just a little bit of algebra. We can put it all in together and have a nice simple readout of this is what the ratio is at any given pH. Okay, so that's just kind of a simplification so you can figure out, okay, what exactly is it right here versus some other value. Okay, so I already kind of talked a little bit about this, but if you haven't seen any videos of putting Mentos in Diet Coke, they're quite entertaining. It's sort of just fascinating that a common consumer products, you can have such a crazy reaction. Definitely would want to do that outdoors in a place and enclosed you don't mind getting messy. Apparently it works best with Diet Coke. Maybe that's might be a viscosity thing or some sort of a density thing. If you've ever worked behind the scenes for any sort of vending that serves Coke products or other soda products, it turns out you can really notice a big difference if you handle the syrup. In high school, I worked at a theater for one summer, movie theater, and we'd replace the movie theater, the stations that fill the Diet Coke and the other Cokes. And the Diet Coke was much, much lighter than the regular Coke for the syrup. It's like these little boxes of syrup that they'd mix with the carbonated water. And it was like, wow, that's so much lighter. So the caffeine-free Diet Coke was like paper almost. It's like, wow, that's like almost nothing in there. And so maybe it has something to do with that. I'm not sure exactly, but for whatever reason, it will work with other ones, but Diet Coke just really has a more explosive reaction with dropping a Mentos in there. And Mentos, I'm not actually sure of the chemistry. They probably have some, they might have some sort of carbonate, something like sodium bicarbonate maybe, or some other thing in there. But I think mostly it's just a rough surface, and it sort of catalyzes the off-gassing of water, or of the CO2, dissolved CO2, into gas form, and it just causes it to happen quickly and just shoots all the water out. So, like I said earlier, when we're considering all those bubbles dissolved, essentially there are bubbles forming because the gas is undissolving, right? It's coming back out of solution. That's the fizzy feeling. It's interesting, and having that much CO2 in there also keeps it somewhat acidic. Turns out that our gag reflex is suppressed a bit by the tanginess of acid. And so if you want to overload some beverage with sugar, the way to make that not trigger your gag reflex is to make it acidic. So that's why we use phosphoric acid and carbonate to allow us to overload our soda with sugar so that it can be addictive and all that, probably. Or maybe just so that it can taste good. Who knows? I don't have a super high view of soda, if you couldn't tell. I mean, it tastes good, and every now and then you just got to have a root beer float. But, anyway. So that's all kind of governed by Henry's law, like we said. A little bit of an elaboration here. We can talk about some concentration of gas dissolved in the water. That would be our bracketed CO2, for example. Could also do that with oxygen or whatever else. And a lot of times we would actually probably write that as CO2 aqueous to denote that. AQ. So that's going to be our dissolved CO2 before it's reacted with water, sort of. So this will give us a value there if we did need to. I mean, it's a 1-to-1 with so CO2 plus water. If we're just looking at the forward reaction, that is 1-to-1, right? It's a 1 here to 1 H2CO3. So it doesn't really matter on a molar basis if we say that as CO2 or H2CO3. It's becoming H2CO3. But that's just the common way to write it, is the CO2 aqueous. And we'll set that equal to this Henry's law constant. We could have a lookup table for that for different gases, or be given a known one for CO2. And that would be, if we put that in moles per liter times atmospheres, which of course there's lots of different units we could deal with if we're dealing with different pressure reporting or whatever. Essentially what that's going to give us is a way to convert from to a moles per liter value from this constant times the pressure, right? So the constant times the pressure, the units have to end up in moles per liter if that's what we're going for. So that's moles per liter provided there, times atmospheres, per atmosphere. That should be the liters and atmospheres should also be in brackets. So it's like moles per liters atmospheres, right? So then the pressure here would be the partial pressure of the gas in atmospheres. So the partial pressure, meaning if what we're breathing right now is 1 atmosphere, the partial pressure of nitrogen, we know nitrogen is what, 78% of the atmosphere approximately. Partial pressure of atmosphere then would be 0.78 atmospheres. So that's just a proportionality, right? So then the partial pressure of oxygen would be about 0.22 or 2.1 or whatever. And then the partial pressure of CO2 then, if CO2 gas in the atmosphere, what is it these days, about 410 ppm or something, parts per million, that's a lot like a percentage, except within a 1 million instead of 100 at the bottom. So that's, if I do this correctly, that'd be 0.4 parts per thousand, 0.041%, I think. So that would be 0.041 atmospheres then, based on that same, that should be 2 further, right? 0.041 atmospheres. Okay, I think I did that right. But that's, we've seen that before. We recognize that's just the atmosphere deal. That partial pressure is a proportionality of the total. And so that's going to give us a pressure, in a sense, of gas in our atmosphere. And of course, that's for an open system. In a closed system, of course, we could elevate it by whatever, maybe we're just injecting a whole bunch of CO2, then we suddenly open it, and if we had, disturbed all that and caused there to be a lot of pressure there, the gas may just come straight out of the solution quite rapidly. Okay, so let's consider then, this book was published a little while ago, probably the first edition, probably 20 years ago or so. So when it was last revised, or whatever edition this was, we had a CO2 in the atmosphere about 390 parts per million by volume, and that typically increases about 1 to 1.5 per year based on human activity. And so right now we're probably a little more than that, but we'll just follow along their example here. So this problem says estimate the pH of natural rainwater, assuming the only substance affecting it is the absorption of CO2 from the atmosphere. Assume the concentration of CO2 is 390 parts per million by volume, and the temperature and pressure are 25 Celsius and 1 atmosphere. Okay, so just take a moment. Don't don't try to solve the whole problem. We'll actually just kind of walk through the book solution and try to make sense of each step. But take a moment to think about what you would need to get there, right? And maybe make kind of your own sketch of a roadmap for how you think you might be able to solve the problem. I'll give you a couple minutes to think about that and write a couple notes. Okay, so we are looking for some equation that can give us H plus, given that we know we have the Henry's law constant in action, giving us some sort of dissolved CO2 in our system, right? So we have some Henry's law, I'm just going to say KCO2 times the pressure of CO2. And we can, if we're given the proper constant there, given the temperature and pressure and all that, we're actually given the pressure here, so we know that's going to be some value, right? This is going to be known, so we know we we know we have some amount of CO2 added, or carbonate added to our system. Okay, but then we come to the fact that we have, so H2CO3, we also know that's in equilibrium with HCO3 minus and H plus. So there's an H plus we can make use of perhaps. We also know that that bicarbonate is in equilibrium with carbonate and more H plus. Okay, so at this point, we should probably be thinking to ourselves, well, shoot, what do we do? We know we have some total, and probably the best thing to start doing is to start finding as many equations of knowns that we have. Okay, so we've written up a couple here. We have these relationships. We know this is known. We know these are known, and in fact, we can look up the K1 and the K2 that we saw earlier. So we know something about these. We need to solve for H plus. In the current state, we could get an equation with K1, and we can get an equation with K2 with the H plus. But there's a lot of unknowns. Obviously, H plus is what we're solving for. That's unknown. The state at which these are in, how much is it in H2CO3 versus the others, those depend on H plus. So we've got to be thinking to ourselves, well, shoot, this is like an iterative mess, right? In some sense, based on this amount of information so far. One other thing we could consider, just based on what we've learned so far as well, we also know that the total amount of carbonate should be the sum of each of these, right? So that would be H2CO3 plus CO3 2 minus plus, and just kind of did this out of order, doesn't matter, HCO3 minus. So the total is going to be all of those. And we know something about the total, so that could be helpful. The fact that we get the total molar units in one form of carbonate means we know that's going to be the total here. So now we have a couple of equations, but it's still not likely going to fix the situation where we have that interdependence of the H plus on which form it's in, and then which form it's in depends on H plus, right? So here's going to be one key aspect of solving our alkalinity equations that you may or may not have been introduced to before, but is actually a common, rule or law of aqueous chemistry, generally. It should be true of almost any condition. It's very rare that this would be broken. And that is that there should be charge neutrality. So I'm going to say charge neutrality concept. That's basically meaning that in a aqueous system, at least from a thermodynamic perspective, it is never thermodynamically favored to have an imbalance of charges. So we're always going to have a net charge of zero if we add up all the ions in solution. In fact, if you ever take a geochemistry course, this is kind of the fundamental principle. Geochemistry meaning kind of the chemistry of natural waters, especially with the mineral content and stuff. You would take a look at all the different minerals, ions, cations, everything, every charged species in solution, and they should ultimately add to zero. So you can check your work to see if you've done a good job quantifying with your analytical instruments for a given solution, if it sums to zero. And in reality, chloride in particular is kind of hard to get a very accurate read on. So usually there's some error, and you're like, okay, well, it's small enough that we think that's just the chloride error or something, or maybe we miss, but if it's a large area, you're like, oh shoot, what did I miss, right? So the charge neutrality concept then is sum of charges in solution should pretty much always equal 0. Okay, so then in this case, we're told that the only things affecting this water is the absorption of CO2 from the atmosphere. So basically nothing else is going to affect it. And so for all the charged species then, with water itself, we know we have H+, we know we have OH-, and then the carbonate species, we know we have CO3 2- and HCO3-. So with that, that's really the only charged species that can exist in this particular case where we have natural rainwater that is utterly pure, right? Maybe in reality, you could have maybe what you would call acid rain, have a little bit of sulfate dissolved, and that would potentially acidify a little further, and you'd have sulfate 2-, all that. But in this case, this is all we have. And so one thing we can say here is the H+ should equal, and this would be on a molar basis because we're talking about the number of charges here, the number of H+ should be equal to whatever it takes to cancel out these other charges, right? Because that's the only positive charge. It has to satisfy all these other ones. So this will be equal to the OH- plus, and because we have a plus here, we know that we are imbalanced from OH equaling H, right? Because we have a plus here means there, unless we had some cation here, it has to be acidic because there's going to be more H+ than there is OH-. So this is already telling us something important about the chemistry here that we could have, deduced just from saying, okay, it's carbonic acid, it's going to acidify a little bit. But mathematically, we see right here, as soon as we add a plus here, we have more H+. So we know that it's slightly acidic or more, right? That'll be very important here in a moment. So we can keep writing this and say that's going to be equal to plus the HCO3-, and then we have to do 2 times the carbonate, CO3 2-, because for every 1 mole per liter of carbonate, that's 2 moles per liter of charge. And that means that has to be 2 moles per liter of H+ to satisfy it, right? So we have to have the 2 there to satisfy the twice charge. So there's, just from our principle of charge neutrality that we just learned just now we have an equation that looks a little more promising. Now we have H+ equals all this stuff, right? We probably still need to include the other pieces, and we'll walk through how the book does that. But that gives us a second, if not third, equation to build a system of equations and solve the problem. Okay, so that's going to be really helpful. Let's see, I think there's one other thing I wanted to say. Of course, we also have our water equilibrium equation. 10 to the minus 14th is equal to H+ times OH-. Okay, I just remembered. So the other thing we can consider here is, because we know we are slightly acidic, at least, I'm just going to write that. We know that something about how much, at least of the bicarbonate there is, or excuse me, the carbonate. So the carbonate, we know, is a very basic pH species, right? In fact, it's at pH 10.33 where this guy is equal to the bicarbonate, where those two are equal. So in fact, if we just flip back a moment to one of these graphs, I'll go back further to the bigger graph. And we say if pH 7 is right around here, right around this line that I have drawn here, how much of it, what fraction is this is going to be carbonate? That's 10 to the minus 3. That's 0.001 at most. Okay? So in fact, it's going to be less than that. So that is way off in the rounding error. And so one thing we can do is, because our solution is at least slightly acidic in this problem solving for the natural rainwater, what we're going to say is that means this is approximately 0 for all intents and purposes, because it's slightly acidic. Does that make sense? Okay, so now we've simplified it quite a bit by saying H plus is essentially equal to OH minus plus the bicarbonate. Then we can get an equation in terms of the bicarbonate and solve given how much CO2 we have in the system. Okay, so that's what the book's solution, I'm going to walk us through here in the next slide, is going to kind of highlight. I wanted to take our time and just take all those pieces out one by one, so that once we look at the solution, that hopefully will make some sense. Okay, so looking at the equilibrium constants, we assume it started without any electrical charge and no net charge is added. That's the charge neutrality principle right there. Okay, essentially it's describing here that charge neutrality, right? So it's that bicarbonate, the carbonate, and the OH minus, and you see here we've got that 2 to satisfy the charges. Then they say, all right, well, given that it's at least, that it's a acidic solution, the way they write it is that carbonate is much less than the bicarbonate, and so they just get rid of it. Right, so that's what I just described a moment ago. This solutions continue, and so from this point, we stop and take and think about what can we do with the system here. And again, we now have H plus equal to OH minus and HCO3 minus. From here, take a moment to think about how you would solve it from this point. So this is going to be kind of an equation we can use to solve. We just have to start ordering things and getting everything in terms of known values. Right. So take a moment, think about what the next step from this point would be. Okay, so one thing we can do is substitute, because we don't know OH minus exactly, we can use this equation here and substitute to say, well, it's going to be a function of H plus, and we might as well put it as a function of H plus so that we can then go back and separate H plus by itself again and solve algebraically and all that. So we can get that portion of the function in terms of H plus. We'll have to do some more simplifying later, but we'll get there. The other thing is we have this HCO3 minus, and so given that we're in some sort of acidic conditions, we can assume that the equilibrium between H2CO3 minus is what we're adding in the first place, and this HCO3 minus is going to be the deciding factor in terms of the equilibrium. So what we can do is get that portion also in terms of H plus and that K1. So K1 that's the products of that equilibrium reaction, which is H plus times HCO3 minus over H2CO3. So we know that, and one thing we can do is essentially substitute in there if we rearrange this. So we can rearrange this to say HCO3 minus is going to be equal to K1 over over H plus. And then we'll have to also multiply by H2CO3. And here, I'm not remembering exactly how the book's doing it, so we'll flip over and let it show us that in a moment. But you could potentially substitute here this H2CO3 based on that. Our equation for the total amount of carbonate is going to be, with carbonate itself, CO3 2 minus, being approximately 0. The remainder is going to be in these two forms. So we could even substitute in here using that total. So let's take a look at how the book is doing the next steps here. So we take the equation here. We get H plus equals this HCO3 minus, plus this 10 to the minus 14th. That's right here. That's this step. From there, they say, well, we take that K1 equation, and we can put this in here. This K1 times H2CO3, they left it as CO2 aqueous. That's the same thing, right? That's as if they put in here the H2CO3. Plus 10 to the minus 14th divided by H plus. So what they've done is they did exactly this. Exactly what we did here, and then inserting that into here, that leaves us with K1 and H2CO3 divided by H plus. And so because it's 10 over the minus 14, 10 to the minus 14th over H plus something else over H plus, you can just add them together, right? Have a common denominator. And so that's where they get, substitute that in, and then they get that common denominator. So then with that, they go on to say, we can multiply both sides by H plus. So that goes over to here. That gives us the H plus squared equals K1 times this H2CO3. Again, they're leaving it as CO2 aqueous, plus 10 to the minus 14. And you can solve from there. So as they continue, they solve for the CO2 gas as we described we can do earlier. They write out the numbers here. 390 times 10 to the minus 6, that's the parts per million, converting that to atmospheres, or that portion. Then they take the constant. This is the constant here. This is the KH. They find that as a value of moles per liter, then put that into this equation, and they get the K1, and they solve. You take the square root, and all those things put into place finally can solve for an H plus value. Turns out that's 2.42 times 10 to the minus 6 moles per liter. Which turns out to a pH of 5.62. So given that neutral water is 7, if you put neutral water, leave it open to the atmosphere, there's absolutely nothing in it, your pH should end up at about 5.6, somewhere around there. Okay, so that was fairly involved. I hope that the individual pieces starting to make some sense. The carbonate system itself, once you get these concepts down, it becomes very workable. Okay, so we have to be able to do the equilibrium chemistry, and a lot of times we'll have to use that principle of charge neutrality. All right. So moving on to hardness then, because that's the carbonate system deals with a good portion of alkalinity. I want to just go ahead and define specifically hardness and alkalinity for us. So hardness would be the concentration of multivalent cations, mostly calcium 2+, magnesium 2+. It would include aluminum 3+. It would include iron in 2+ or 3+ forms. But usually in a source of water, if we've got a lot of iron in it, we're probably trying to remove it. And calcium and magnesium are usually the ones left that aren't really any human concern, but they will cause mineral deposits. So we see a pipe here, the cross section, where we've got lots of mineral deposition there. We do actually want that compared to operating in a corrosive environment where we would corrode the pipe away. But we want to try to minimize that so that it's slowly adding minerals, right? We don't want to have to dig up our pipes every 5 years. We would rather be able to get away with 100 years before we had to dig up and replace pipes, right? As convenient as it would be to remember where we put the pipes 5 years ago compared to 100 years ago, it's still a very big cost. Okay, so that's hardness, really described mostly as calcium and magnesium, or quantified based on those two. Alkalinity then, I guess a good definition would be the measure of water's ability to accept acid without changing pH. And you might think to yourself, well, how's that possible? Buffer solutions and the carbonate system being one of them, can give us a condition where we have to add a lot of acid before the pH starts to change. And if you think back on our equilibrium with H2CO3 and HCO3 minus, when we add acid, we are causing a conversion here in addition to changing the amount of pH, the amount of H that's present. That conversion here of this addition of H plus means that we're adding acid without necessarily changing, or not changing as much, the actual H plus value. So there's a variety of stuff in solution that can do that, and this relates very much to that charge neutrality principle. For example, if you add carbonate in the form of calcium carbonate, let's say you end up with, it technically is in equilibrium if it's a solid, and you're getting CO3 2 minus and Ca2 plus, and then you add acid, what's going to happen is you're ultimately converting this carbonate into carbonic acid, and then it's escaping as CO2. And what you're left with then is a +2 charge. If all of this charge went away as you're adding acid, you're left with a +2 charge, in our charge neutrality equation, it's H plus the positive charges, right? So that's actually preventing, like that whole process prevents that acidification of your solution from driving the pH down, because those H pluses are being used to create water and CO2 gas. Okay, and then the system is still balanced because we've on the basis of the Ca2 plus, meaning there has to be some OH minus to counteract it. So it's a little bit loopy when you're like trying to think through it all, but adding something like calcium carbonate definitely has a buffering effect on a system. This is also, a similar thing would be true of sodium bicarbonate, NaHCO3 going to Na plus and HCO3 minus. Actually, it might actually be Na2CO3. It might just be that, right? Maybe both exist. I'm doubting myself right now. Oops, that's not a 2. I'm sort of second guessing myself right now, but sodium bicarbonate is baking soda, right? Yeah, that's in every household. That's important for baking for very similar reasons, right? Controlling of the pH and things like that. Potentially adding the CO2 into a bake that's going to then create CO2 gas in the bread or whatever it is to make more bubbles, to make it more airy, whatever desired effect. That's part of why. It's right there. Okay, so let's talk about these equivalents that we mentioned earlier. I think this is approximately where I wanted to get to. So let's go through this slide, and I think that'll probably be it for today. So when we say as calcium carbonate, essentially what we're talking about is either molar equivalents of charge, or we're talking about equivalent weights, which is a way to deal with equivalent charges, but rather than as a mole per liter basis, as a comparison to a mass, a known mass, which would be our calcium carbonate. So an equivalent weight would be the atomic or molecular weight of some species divided by N, where N is the charge of that ion. So we could say that the equivalent weight, if we were to write this as an equation, would be the molecular weight or atomic weight divided by charge. Okay. So another way of describing that charge is the number of hydrogen atoms required to replace that cation. So I was talking earlier about replacing or accounting for the charge within our charge neutralization concept. A Ca2 plus, how many hydrogens would that take? That would be 2 H plus to counteract that same amount of charge, right? That's just what N means here. Okay, so to describe then the equivalent weight of CaCO3, calcium carbonate, we could say that's going to be the molecular weight. Calcium is 40, carbon is 12, and then we have 3 oxygens. We add those together and we get 100. Nice and easy, nice and convenient. We take that 100 and divide it by the Ca2 plus, right? That 2 plus is coming from the Ca2 plus. So 100 divided by 2 is 50, and that, if we look at the units, that's grams per mole divided by equivalent charge on the bottom. And so what we end up with is here 50 grams, and I think that's charge per mole, right? Yeah, it's per mole. So what we'll end up with is 50 grams per equivalent charge, or more often we represent it as milligrams per milliequivalents. So that's some amount of mass per molar charge. So it's a lot like a molecular weight, but it's in the sense of charge. So it's like moles of charge. So it's like instead of molecular weight, it's molecular charge per weight, or molecular weight per charge, rather, right? So it's very similar to the molecular weight concept. We're just normalizing by charge, okay? So the equivalent weight for CaCO3, we're dealing with milliequivalents. That's where the equivalent weight comes from, right? That would be 50 milligrams per milliequivalents. If we were to just look at the Ca2 plus here, we would take it 40.1 divided by 2, approximately 20 milligrams per milliequivalent. So you can do that for anything, right? You could take the milliequivalents of X is going to be the concentration of that X. If you were to solve for the actual like milliequivalents per liter here, so to get the per liter, to solve for a concentration of charge, so to speak. And again, this is in the context of thinking about hardness, how much hardness is in there, or how much alkalinity is in there, is the context of when we'll use these. Well, maybe we want to know the milliequivalents of X. The way to solve for that would be to take the concentration of X, milligrams per liter. And if we're using milligrams, then we can associate it with this milliequivalence here, milligrams per milliequivalent. So this is just like converting from mass to moles, except we've added in that equivalence aspect. Right? So it's the same exact process with a different flavor. Right? So we've got that divided by, normally we take the concentration in milligrams per liter and divide it by the molecular weight to get the moles per liter. And we could do that with millimoles per liter, with milligrams and all that. Here we're going to say concentration of X in milligrams per liter divided by the equivalent weight of X. And if we take the units here, this is milligrams per liter divided by milligrams per milliequivalents. That's going to give us that milliequivalents per liter. Okay, so in the end, it's very simple, very straightforward. You've done this all the time. But I'm just trying to make it clear that where these components are coming from so that we can get this stuff straight and squared away. Now so that's an equivalence. The last part here is if we want to express it as a milligrams per liter as CaCO3. This is commonly done. It's just sort of a shortcut, right? It's a common shorthand to get back to a mass units, even though we're really talking about molar units. And we do that because we can pretty conveniently with calcium carbonate, again, so important with our alkalinity systems. So basically anybody working with alkalinity or hardness is going to care about calcium and carbonate, right, in some sense. So it's just very convenient. It rounds to 100 or 50 if we take that divide by 2. So what we say is if we have some milligrams of X per liter and then we describe it as CaCO3, what we're saying is we have some concentration of X in milligrams per liter and we multiply it by 50 milligrams of CaCO3 per milliequivalent. So we're just referencing CaCO3 as a default normalizer agent in a sense. And we divide that by the equivalent weight of whatever X that we're dealing with. So it's really just taking the equivalent, the MEQ per liter and multiplying it by 50 milligrams CaCO3 per milliequivalent, which gives us the milliequivalents will cancel, gives us milligrams CaCO3 per liter as our units, even though we're describing something else. We could be saying magnesium. We have 50 50 milligrams per liter of magnesium as this other thing. It's kind of weird, but it's just the way it's done. And once we start solving some problems, it'll start making a little more sense as to, we can compare them all in this manner, and it just gives us a convenient mass handle to deal with it. So a little complicated, feels more complicated than it needs to be, but overall it is simple stuff. Okay, so I'll leave you there. We'll come back to this next time and work on water softening at that point. All right.